Hello friends, today we are going to talk about a wonderful process called electrochemical machining process. Now, as you already know, it is not something, some machining process that is actually a traditional machining process. It is a non-traditional, unconventional machining process, isn't it? So in ECM process, first of all, we need to see that the electrochemical machining process, what this name suggests, electrochemical machining process, that means it is combination of two words. Electrochemical is combination of two words, one is electrical and the chemical. So that means just like other non-traditional machining processes, here you are going to use the electrical energy, and you are going to utilize the chemical energy, isn't it? You are going to use electrical energy plus chemical energy simultaneously, and in order to remove a layer of the workpiece, or in order to perform the machining operation, isn't it? It's a wonderful process, my friends. And if you have a look at ECM, you will see that you will find that it looks very much familiar with one of the processes we use to learn in our schools. Have you heard of electroplating? Yes, isn't it? Yes, in schools or in earlier days, we have seen what is electroplating and how the electrolysis is performed actually. So what happens there is that there are two terminals, and there is one workpiece, right? Let me take the example of jewelry. So in jewelry, you must have seen that it is plated, gold plated, it is silver plated, like that, isn't it? So the jewelry would be actually made as the negative terminal, isn't it? The negative electrode. The negative terminal is attached to the jewelry, and whereas there is a small strip of gold or silver or whatever material you want to coat on that jewelry is made to be a positive electrode. Getting the point? Yes. And when you switch on the circuit, then what happens? And one more thing, I forgot to state one thing, that this system is actually dipped, it is submerged in electrolyte. Isn't it? Electrolyte is a very essential component, we cannot afford to miss it, isn't it? So what happens is that there is a gold strip, there is a jewelry, gold is attached to the positive terminal, jewelry is attached to the negative terminal, immerse in the liquid called electrolyte, switch on the circuit. Now what will happen? You will find that the gold strip is actually getting dissolved in the electrolyte, and it is getting coated over the negative terminal or the jewelry, isn't it? So this is electrolysis or electroplating technique, isn't it? And in electrochemical machining operation also, you are going to witness exactly the same thing happening. But here the area of interest changes. There, the area of interest was the jewelry, which was the negative electrode, or it is made cathode, isn't it? But here, our area of interest will be the anode. Why? Because the material is getting dissolved, it is getting removed from the anode, and it is getting deposited over cathode. So if I want a workpiece, how good it would be if I make the workpiece as anode, and then by certain means, if I do something, I arrange few systems in such a manner that I can regulate the work, regulate the material removal rate from the workpiece according to my wish, according to my requirement, isn't it? So how good it would be? So for that, what I need to do? I need a tool of some shape. Okay, I will be making a tool of some shape. Actually, it is a complementary shape that we need to generate over the tool, and then there will be a workpiece. The tool will be connected to the negative, workpiece will be connected to positive, and now when the tool is going to interact with the workpiece, this complementary shape will actually generate it over the workpiece. And now what will happen? As you know, this workpiece, because it is anode is the material from anode gets deposited, it gets removed and gets deposited over cathode. So exactly same thing is going to happen. I am going to remove the work or the material from the workpiece, and it is I will remove it, but I will do something, I will do some arrangement so that it doesn't deposit over the cathode, because the cathode is nothing but it is a tool of one respective shape, one specific shape that is made the complementary shape, isn't it? And I don't want the shape to get distorted, because the material, if it gets deposited over the cathode, it is going to lose its accuracy. So I don't want it to happen, and for that I'm going to do something. I'm going to do some arrangement. We will be talking about that soon, isn't it? So this is a overview of the electrochemical machining process. I just told you about a relationship between the electrochemical machining and the electroplating, or electroplating technique, isn't it? Yeah. Now, before we proceed, I want you to have a look at a small video clip I have brought for you. It will give you a better idea. Let us have a look at the video clip right now. Yes. How electrochemical machining works. Okay. So you can see here that there is a packet or an envelope of the electrolyte, and you can see that there is a machine tool, and the blank is dipped into, it is submerged in the electrolyte. And what happens when you switch on the circuit, the material from the anode, which has been made a workpiece, it starts to dissolve, and it simply gets removed from the workpiece. And also you can see the complementary shape of the tool, and the tool is fed towards the workpiece, and as it moves towards the workpiece, the more and more material starts to dissolve, and that material simply gets removed from the workpiece, and your workpiece is designed, it gets a new shape altogether because of the shape of the tool, isn't it? It's a wonderful process, it's a very beautiful process actually. So this is what actually about electrochemical machining process broadly, isn't it? Now we will enter into the specifications of the same process, and we will analyze it in detail. Very good. Alright my friends, now you can see that there is a schematic diagram over here, and now we are going to talk about the process step by step, and you will observe how the process actually is performed. Okay, so let us have a look at the components first. Let us see the construction. You can see that this part, this is a enclosure, and this is known as fixture. This is fixture upon which a table has been mounted. You can see the table. And what this table does, this is actually used for holding, for housing the workpiece properly, securing the workpiece properly. You can see this thing is a workpiece, and I want a cut like this in the workpiece, and for that what I need to do is I need to have a tool of a complementary shape. So for this thing I can see that there is a tool of a complementary shape. This is the tool over here, isn't it? This is the tool over here. And usually these tools are made hollow. I mean, there is a small, there is a envelope path, you can see, there is a small gap, and through which the electrolyte can be fed. There is a small path, a very fine path that is made in the tool, okay, and which is actually used for supplying the electrolyte. And you can see that there is a container for the electrolyte. A suitable electrolyte is chosen depending upon the workpiece and the tool. And so this electrolyte is fed in this manner from the container. You can see there is a pump over here. So this pump pumps the electrolyte from the container, and you can see this part, this component is actually the filter. Why? Because the electrolyte is going to carry away all the heat and the debris of the workpiece, because this workpiece is going to get machined out. A layer is, the material is going to get removed because of the process, and this debris is going to get carried away by the electrolyte, and that is why we need a filter so that it can simply filter the electrolyte, and you get a pure electrolyte without the debris actually. So this is actually the filter. This is the filter over here. And now what is this? What is next? This is your pressure meter or pressure gauge. Pressure meter or pressure gauge. Okay. You will call it meter, better. Okay. It is a pressure gauge, pressure meter, or it is actually basically used for the pressure regulation, nothing else. You actually control the pressure of the electrolyte with this valve. And the component over here that you can see is the flow meter. You can control the amount of material going to flow in, amount of electrolyte going to flow in. Simply you're controlling the volume. So this is flow meter. Okay, how much volume should go in is controlled by this component, and from here you can see the electrolyte goes into the tool and it comes out of this small exit located in the tool itself. And now what happens is that for ECM process, the gap between the tool and the workpiece is actually very important. It is the most essential part. So if you are capable of, if you manage to control the gap between the tool and the workpiece, then your operation will run smoothly and you can obtain the accurate results. But if there is a small deviation in maintaining the gap, then you might not obtain a finished workpiece. Okay, so basically what I mean to say is that the gap between tool and the workpiece is actually very important. And so for that, what we do is that we have a servo controller over here that senses the gap increasing between the workpiece and the tool, and accordingly it feeds the tool continuously towards the workpiece while maintaining a suitable gap between them. And this gap is actually very small. You will see it is of the order of few mm, not even 1 mm. Actually, it is even smaller than that. So that small gap has to be maintained always, and for that we use an automated system. It is known as a servo controller unit, or simply you can call it a feed unit. Okay, this is a feed unit, and over here you can see this is a power supply. And as you know that the workpiece should be negative or positive. It should be positive, isn't it? Yes, it should be positive, and the tool has to be made negative, right? So this is more or less about your ECM process construction, and now we will start the discussion about everything about the complete process along with the specifications, right? Okay, now my friends, what happened was that Michael Faraday was the first person to discover that if two electrodes are placed in a bath of electrolyte and the circuit is switched on, he realized that the material from the anode gets deposited over the cathode, right? And this material removal rate actually is a function of few things. What are they? The current pass, how much amount of current is being passed in the circuit, the amount of time for which the current was passed, right? The atomic weight, and the valency of the material. Getting the point? So this is actually known as the Faraday's law, and you can see it on your screens also, that the first point says that Michael Faraday discovered that if two electrodes are placed in a bath containing liquid and a DC potential is applied across them, then the metal can be depleted from the anode and placed on cathode, right? And you can also see the second point, that here the material is removed, hence electroplating is reversed by making the workpiece's anode. So in electroplating, what you were doing is, you were actually depositing the material over cathode, but here you're depleting the material from the anode, isn't it? So the areas of concern have changed. You can also see the next slide. The next point says the metal from anode is dissolved electrochemically, and hence the MRR is based on Faraday's law, will depend upon the atomic weight, fine, the valency, fine, current passed, and the time for which it was passed, and none of the other parameters. Isn't it? Yes. Very good. Now, next point is, at the cathode, only hydrogen gas is evolved and no other reaction takes place. So the shape of the cathode remains unaffected, right? Now, the next point. Next point says, my friends, that thus the ECM process can now be conceived as a process involving a tool cathode, fine, a tool cathode, yeah, which has a complementary shape of the part to be produced and the work to be made as the anode. Isn't it? Yes, the workpiece has been made as anode and the cathode is nothing but the tool. Now, a small gap is maintained as we discussed. In the small gap between the workpiece and the tool, a suitable electrolyte is pumped at high pressure. Would you agree with this thing? Yes, absolutely, because that is why the electrolytes are being used for. What is the function of the electrolyte? It is actually, closing the circuit, because the tool is going to be at a certain distance apart from the workpiece, and in between them there will be no conductor. So who will fill the gap? The electrolyte will come and fill the gap, isn't it? And obviously the electrolyte has to be a very good conductor of heat and electricity. Further point, yes. Proceeding further, the electrolyte has to be carefully selected such that they provide necessary reactions without plating the cathode. Very good. Right. Now also you can see that in the slide, the properties of the electrolyte have been mentioned. Right. The first property you can see is the high electrical conductivity. Obviously, we discussed just right now. The second point, it should be low in viscosity. Its viscosity should be low. Why? Because, my friends, there is a small gap which is maintained between tool and the workpiece. If the electrolyte is viscous, it might not enter into small gaps, and it will not be that fluidic also. So that is why the electrolyte has to be made fluidic, extremely fluidic and extremely non-viscous. Now the third point says it should be chemically stable. It should be chemically stable. It should not be corrosive. It should not be toxic. It should not react with the workpiece or the cathode material. Very good. The fourth point says exactly the same thing. It should not be corrosive, non-toxic. That means it should be chemically stable. And the next point, the most important one, because everything is all about the money and the finances, isn't it? So in order to make it a reasonably economical process, the electrolyte also has to be economical, right? It should not be extremely expensive. There are a few examples you can see on the slides, that the sodium chloride and potassium chloride, also sodium nitrate, are few electrolytes that we use commonly for ECM process. And let us have a look at the tool materials also. If you want, see, the common examples are aluminum, copper, brass, titanium, stainless steel. All these are the fine examples of tool material. Actually, the tool materials are expected to have a very good thermal conductivity and the electrical conductivity, and also they should be stiff, they should be easily machinable, and they also should be stable. That means they should not corrode, isn't it, in that environment. So that is why these are the few properties. That is why the tool materials are made using all these metals, right? They fulfill one or the other properties of being a tool material. Very good. Let us proceed further to the ECM parameters. Right? Now we are going to talk about the ECM parameters. This is the most important slide for the ECM process, because it is going to talk about the specifications. Let us have a look. The current that you are going to pass through the circuit is going to vary between 50 to 40,000 amperes. It's a lot of current. It's a very high value for the current. Yes. Now the current density, you can see it varies from 8 to 223 amperes per centimeter square. Right. Voltage is quite, it's not that high. The voltage you can see is between 4 to 30 volts DC, right? And the gap is extremely small. You can see it is 0.025 to 0.75 mm. It is not even 1 mm. So that means the tool and the workpiece are going to be extremely close to each other, and that gap has has to be maintained continuously, which is even more important, isn't it? It is even more difficult task to achieve, and for that we use the automated process, the servo controllers you can see over here, the feed unit. This is what we use it for. Right, very good. Now the electrolyte velocity, what should be the velocity for the electrolyte? Because this electrolyte is going to carry off the heat and the debris, the material that has been machined out of the workpiece, it has to carry away that, isn't it? Otherwise what will happen, this the debris or the workpiece material removed has this tendency to get coated over the cathode, isn't it? But do we want it to happen? No, I mean definitely not. Because the cathode is a tool material, it has the shape of the cathode has to be maintained at any cost, because it is going to define the finish and the accuracy of the workpiece, isn't it? And that is why the electrolyte has to be fed at a velocity ranging from 15 to 60 meter per second. And the electrolyte pressure also has to be maintained between 0.069 to 2.7 ampere. Very good. Now the electrolyte temperature is also an important parameter. It should not lie above 65 and lesser than 24. That means it should lie between 24 to 65 degrees Celsius, right? And the feed rate, you can see it is 0.5 to 19 mm per minute, but this feed rate is going to vary. It is not it is not compulsory for the feed rate to lie in this range itself. It can have different values for different materials, depending upon the tool, depending upon the workpiece, depending upon the cathode. Depending upon the electrolyte, and depending upon the voltage, the current. There are several parameters upon which this feed rate could depend upon. Right? Very good. So these were the few ECM parameters that you have to you can note it, right? It's worth noticing. Yes. Right. Now, if you talk about the questions asked in the GATE exam, what kind of questions are asked from ECM? Because this is what we are here for, isn't it? To study about the ECM from the point of the GATE exam. Very good. So what to do? I am going to give you few numericals and we will solve it along. And but before that, let me give you few datas, few formulas that are used to calculate few questions here. Let us have a look. Alright, so the first formula that you need to learn for ECM is the material removal rate. How it has to be calculated? It's very simple. You have already we have already discussed about that. The MRR depends upon the Faraday's law, isn't it? And it states that MRR will depend upon atomic weight, the current, the valency, and there is a constant called Faraday's constant, isn't it? Yeah. So this is the MRR given in the unit should be kg per second. This is the MRR, and where, just for the record, I am telling you where A is your atomic weight, I is current, the Z is valency of the material removed, isn't it? And F is the Faraday's constant. Yes, it is Faraday's constant. And what is the value for Faraday's constant? Usually it is taken as 96500, isn't it? Yes. So this is the formula for calculating the material removal rate, if it is asked in kg per second. But if a volumetric MRR has been asked, then what you are going to use is, the formula changes to this one, AI by rho ZF. Now instead of simply ZF, there is one more entity has been attached. It is rho ZF, and the unit is going to be mm cube per second. It is mm cube per second. Right? So these are the two formulas that have to be used extensively, isn't it? Very good. Now what happens, my friends, is sometimes this is a very common kind of problem you will witness in the GATE exam. Also, my friends, in the GATE exam, it is a very common question they ask is that what is the MRR for an alloy, right? Because this is the volumetric MRR for one single element, for one single metal, and whose AI, density, the valency, everything is known to you, isn't it? But if suppose this is not a single element, now you are machining electrochemically an alloy where it is a combination of three elements, A, B and C. A is having a total percentage by weight is 30%, let's say. Similarly, B weight percent is again 30%, C 60%, like that. I'm sorry, 40%, right? Now, how you are going to calculate the MRR for the alloy, isn't it? So what you are going to do is, you are going to restructure your MRR formula. In those cases, the formula changes, it is not even changing, it's simply a rearrangement. You can see that it will be given by x1 I by rho f x1, then x1 z1 divided by a1, right, for the first element. What is x? X is the percentage. Suppose we were talking about A, B and C, 30% A, then z1 the valency, atomic weight. Similarly for x2, which is again 30% for element B and A2. Similarly the third, x3, 40%, then z3 by A3. In this manner you can solve for the alloy, isn't it? And this kind of problems are asked quite a number of times, isn't it? They are actually more common, they are more popular from ECM process, right? So what we are going to do is, we will try to use these formulas with the help of few numericals, okay? And yeah, so let us proceed to the numericals. Alright, now you can see one numerical problem on your screen. This is a GATE question from 2009, from year 2009. The electrochemical machining is performed to remove material from an iron surface of 20 by 20 mm under the following conditions. Fine. So the area has been given to you, it's 20 by 20. Now the inter-electrode gap, the gap between tool and the workpiece is 0.2 mm. It's very small. Supply voltage is 12 volt, fine. Specific resistance of the electrolyte. What is the specific resistance of the electrolyte? It's 2 ohm centimeter. Atomic weight of iron 55.85. Valency of iron 2. Faraday's constant is 96540. Fine. Now what they ask is, you have to calculate the material removal rate in gram per second. Isn't it? In gram per second. Yeah. So what you're going to do is, you're simply going to use this formula. We know this MRR is actually AI by ZF, right? Now what is A? A is A for the iron, it is 55.85. It is 55.85. Now what is I? I is the current, right? But unfortunately current is not given to us. So simply we will write I as I itself. What is Z? The valency. Valency is 2. F is Faraday's constant, it's 96540. 96540. This is the MRR. Fine. But how to calculate this I? For this, I can see how we can have a look here. The voltage is given to you and the resistance of the electrolyte, the specific resistance of the electrolyte has been given to you, isn't? So what to do now? We can calculate I by using the Ohm's law. V equals IR, isn't it? V equals IR, that means, therefore, I is what? I is V by R. Right, now what is V? V is given to you as 12 volt, fine. Now what is the R? It is the resistance, isn't it? Resistance. But what is actually the resistance of the electrolyte? For that, my friends, you must have learned one formula in schools, that this R is given to you as density into, or I'm sorry, it's not density. Okay, I'm taking it once again. So in order to calculate this R, what you're going to do is, you must have learned one formula in schools also, that R is equal to rho H by A. Now what is rho? Rho is nothing but the specific resistance of the electrolyte. Now what is H over here? H is nothing but it is the inter-electrode gap. And now what is A? A is the area, isn't it? A is the area. Now what is the area? Area has been given to you, it's 20 by 20, right? So what we are going to do is, rho has some value, it is specific resistance of the electrolyte, it's 2 ohm. And what is H? It is 0.2 mm, it is 0.2 mm. And what is A? It's 20 by 20. So when you calculate this, what should you get? What is the value that you obtain? It is 1 into 10 to the power minus 3. But one thing I can see that this specific resistance of the electrolyte has been given in centimeters. So do I need to convert it into something? What we will do is, we will convert it into mm. So this 2 centimeter should become 20 mm, isn't it? It should become 20 mm. So that is why it will become, see, 20 will get cancelled out, and you will get 10 to the power minus 2. It is better to write it in this manner. Okay, fine. So friends, you have got this value, R equals 0.01, isn't it? Yes. Now what to do? Let us put this value over here. I is equal to 12 by 0.01. What is the answer now? So 12 divided by this, it's 1200. It's 1200 ampere. This is your answer. Right? Very good. Now, yeah, so I think we have, okay, we have just got I, actually we have to calculate the MRR, isn't it? I forgot, my bad. Okay, MRR is actually this thing, so 55.85 times 1200 ampere divided by 2 into 9650040. So what is the value? Let us calculate. Yes, I am getting a value of 0.3471. 0.3471. Isn't it? So, does it match with any of the options given to us? Yes, it matches with 0.3471. Yes, and so I think the option A should be correct. 0.3471 is the correct answer. Right? So, this kind of problems are also asked, and now we will have a look at the other kind of problem I told you about the alloy, isn't it? Yes. So let us proceed further. I hope that this is clear, and we can proceed. Yeah. Alright friends, let us move to the second problem. You can see the given data has been mentioned over here. This is a gate problem from year 2002, okay, and you can see that the alloy it's an alloy of three elements, the cobalt, nickel and chromium, and their respective percentages by weight has also been given, 18%, 62% and the 20% respectively, okay, and also the atomic weight and the valencies are have been mentioned over here. Cobalt 58.93, valency 2, nickel 58.71, valency 2, chromium 51.99, valency 2, okay, and the Faraday's constant is given to you 96500, current is 500 amperes, density is 8.28 gram per cc, okay. Now what we need to do is we have to calculate the MRR, okay, and as you already know, we discussed that MRR for these cases is nothing but I divided by rho into F x1 z1 by a1 plus x2 z2 by a2 plus x3 z3 by a3. That's all. Let us put down the values. MRR is equal to I is 500 amperes, density is 8.28, F is 96500, yeah. And what is x1? What is x1? X1 is the percentage for the first element, the chromium, cobalt. Z1, it's 2. What is atomic weight? It is 58.93. The second one, x2, is 62%, 0.62. And what is the valency? It's 2, again, it's for nickel, right? And what is the atomic weight? 58.71. Now x3 is 20%, so 0.2. Z3 is 51.99. Oh sorry, Z3 is the valency, so it is 6. And atomic weight is 51.99. Now if you calculate this thing, we will get the MRR, the volumetric MRR, right? So let us calculate. It's 500 divided by 8.28 times 96500 times 6.1 into 10 to the power minus 3, or you can write it as 0.0061 plus this term 0.021, and now this term, final term, 0.023. Now add up, solve this up, you will get 0.01243. It is centimeter cube per second. So this will be your MRR, 0.0123 cubic centimeter per second, right? So I hope that this problem is very clear to you. This is nothing but this is a problem for the alloys, right? So you should be aware of both the kind of problems being asked. They might ask you to calculate the MRR for one single element or a combination of elements, an alloy, right? So I hope that both the problems are clear. Along with the process, we discuss about ECM process, right? And so that would be all. And thank you very much. All the best.